All right, hello everyone, welcome to this video. This is going to be about thermal expansion. And one of the interesting phenomena in physics is that a piece of material can actually change in length. It can actually expand when it heats up and contract when it cools down. And in this problem, we would like to analyze how much does the length of an iron beam increase when it is heated up by 15 degrees Celsius. So let's just visualize the problem. Here is a beam, and this is going to be at some initial temperature. And when we raise to a higher temperature, you just put like T1, and here's T2. When we raise to the higher temperature, the beam will get longer by some change in length, delta L. And its initial length, we'll just call L naught. And so our goal is to figure out what is this delta L that occurs when we undergo the temperature change, delta T. Okay, so we can put in some given information that we have. We have the initial length of the beam as 10 meters. We have the change in temperature as 15 degrees Celsius. And then we have the property of this beam that controls the effect, called the coefficient of thermal expansion. That's a long one. And that's the Greek letter alpha, by the way. This is going to be 12 times 10 to the minus 6, and it has no unit in this case besides inverse Celsius. And it's written in this peculiar format of 1 over Celsius degree to indicate that it's per a change in temperature, not divided by an absolute value of temperature. So essentially what we're going to end up doing is multiplying alpha by T. You can see that this is a delta T, so this is a range in temperature. And actually I could have even written this one too in the same notation. And then that's why all these Celsius degrees, they're basically referring to delta T's, not individual T's. Okay, so the formula, and it's an empirical formula, is that the change in length is equal to the original length times the coefficient of thermal expansion, and then times the change in temperature, like so. So basically just multiplying everything together. We can now put in our numbers and we'll check our units. So here's 10 meters. Here's the alpha of 12 times 10 to the minus 6 per Celsius degree. And now the change in temperature of 15 Celsius degree. You can see the Celsius degrees are going to cancel out, and we're just going to get a number out in meters. So the change in length will be essentially just multiplying all of these together. It will come out to be essentially 1.8 times 10 to the minus 3 meters, which we can express as just 1.8 millimeters. Okay, so just one quick note here, guys. This formula is just what's called an empirical expression. It's not a deep fundamental law of physics. It's simply an approximation that allows you to estimate what is the change in length for a change in temperature from an initial length. And the key assumption here is that this alpha coefficient is in fact a constant. In reality, over a long change in temperature, this alpha itself could depend on temperature, and then we're into having a more complex expression. But for small changes in temperature, this is a good model for thermal expansion. All right, so interesting to note, 10-meter long beam. That's pretty long. That's like almost 3 stories tall. And we can see that such a long beam, it'll only expand by 1.8 millimeters, at least for iron, which is the material we use the alpha coefficient for. So it's not nothing. It's definitely something. And when people build structures, they have to take into account this thermal expansion so that the parts don't damage themselves when they undergo this expansion, press against each other unnecessarily. All right, well, that's it for now. Thank you guys for watching, and I'll catch you in the next video.